So hello everyone. I've seen a couple of names that I know on the chat, so hello to all of you. For those who don't know me, which I guess it's the majority, I'm Carlos, Carlos Garcia. I work at Institut Pasteur and at Universidad Carlos III de Madrid. And I'm going to present the plugin that I developed with for Fiji and for more Java-based software with many other people called SAMJ. And the idea is that SAMJ enables fast annotation using foundational deep learning models, AI models, on Java-based bioimaging software. So on this presentation, I'll first try to give on this workshop, I'll try to give a small overview of a short overview of what is a transformer, which I guess that many of you will know, but just in case. Then I'll try to explain a little bit what is the segment anything model, SAM, and its variants. And finally, I will go over the actual plugin, and I have a couple of hands-on activities. First, I'd like to give you the opportunity to install the plugin now, because in that way we can try to use it at the end. Its installation in Fiji should be quite easy. If you have Fiji installed, you just can go to the update site. Just look for SAMJ. Click on the update site, apply and close. Restart Fiji, and once it is restarted, you should be able to launch the SAMJ plugin. I'm telling you this now because the installation might take, depending on the hardware, between 2 and 20, even 30 minutes. So if you install now, you may be able to use it at the end. I'd recommend installing SAM2 Tiny, because it's the SAM2 Tiny or Efficient VIT SAM-L2, because they are the ones, the lightest one, the ones that are more easy to use in any computer. So they should work on any laptop. Okay, now let's go about the transformer. The transformer, if you don't know, it was introduced in 2017 by Vaswani et al. By Google Brain. And at the beginning, it was just presented as a new deep learning architecture or AI architecture just for language translation. And this was quite an understatement, because it's currently the cornerstone of all the artificial intelligence revolution that we are experiencing right now. It powers ChatGPT, which I guess almost all of you will know, but it's also used for music generation, such as Suno or Udio and all these projects, but it can be used in other tasks, such as protein folding. It was introduced in the paper, Attention is All You Need, and it had 3 key contributions. The first one was self-attention, so it allowed parts of the data to attend to other parts of the data. Then they had the multi-head attention, which allowed each part of the data to attend to several things, other things in the data, not to just one. And then positional encoding, which gave a sense of order to the data structures. I'm not going to go in detail over this because we are on a short talk, but I'll leave you. I think I will try to share the presentation after in some way, but if not, you have these 2 resources, which if you want to understand better the transformer, they are quite useful. I highly recommend, if you're interested, watching this series of videos by 3 Blue 1 Brown. That's for those who don't know this YouTuber. It's a YouTuber that creates really good content for math in YouTube. So after seeing all the advances that the transformer gave in the natural language processing field, the computer vision researchers try to use this architecture to improve the state of the art or the computer vision task. And that's why Google again introduced the VIT transformer or the vision transformer, in, I think it was 2019, which is architecture that used transformers for computer vision tasks. It managed to outperform convolutional neural networks, or CNNs, which were the previous state of the art, but it required huge amounts of data and parameters. So the models needed to be quite big. And this is the architecture. It's quite straightforward. Once we understand the transformer, what they do is basically to divide the image into patches and then just try to find the relationships between these patches. As we see, as I said before, the transformers outperform the previous methods, the convolutional neural networks, but in order to do so, they require huge amounts of data. So in this case, it's not until they use 300 million images that they are able to surpass CNNs, and the models had to be quite big too. So here are more resources I'll share it later to learn more about BITs, transformers in vision. But I really want you to understand that transformers are really data hungry. So in order to make a transformer model, whether it is text or something like ChatGPT or something like SAM for vision, you need lots and lots of data. This is bad, but on the other side, as long as you have enough data and as long as your models are big enough, transformers basically can learn almost infinitely. That is that as long as you have new data, they will keep learning and keep learning and keep learning. They can basically learn relationship between anything and everything. They can learn relationships between words in text, between pixels in images, between audio, and they can even learn relationships between amino acids for protein folding. So looking at this, we can understand how in the natural images world, so that is for images that you may have on your phone, images of dogs, images of cats, of cars, whatever, the state of the art for computer vision is led by transformers, image classification, semantic segmentation, object detection, whatever. But when we get to the state of the art in more niche, more specific task, where data is not so available and more difficult to find data, we see how for example, in medical image segmentation, which the concerns of data privacy and all that makes more difficult to share the data, the images, the CNNs still are the kings in this case. So if there's tissue images, CT scans, nuclear images, whatever, the CNNs still can take an important part of this field. So again, I know that I'm repeating myself, but I'd like to get this message straight. In order to be able to get transformers to perform good, we need millions of images. So if you want to tackle an image processing problem with your own data, it might be better to use CNNs. So, however, there's people who have huge amounts of data, such as Facebook or Meta, which can create really good models that can work for almost anything. And that's where the segment anything model came to life. The segment anything model was a model released by Meta AI, previously known as Facebook, which introduced this model, this state-of-the-art model, that is able to do promptable segmentation. That is not the segmentation of a whole image. You need to provide a hint, a prompt that can be a bounding box or a point of where the object is in order to segment an object. But this model is basically capable of segmenting any object in any type of image. So the good thing of this model is that it seems to have the concept of an object. It's able to differentiate an independent object from the rest of the image. And these are the key aspects of this model. Again, this is promptable segmentation. It has real-time interaction. So once you have encoded, I will explain what encode is later, an image, you can basically click on any object on the image and the model will be able to segment it very fast, almost in real time. And again, as it is a transformer, a vision transformer, it was trained on 1 billion masks shared between 11 million images. So that is a lot of data and lots of diverse images, of high resolution images of many, many modalities. And this is why it's able to perform so well on almost any kind of image. As I said before, it's based on the VATs, on the vision transformers. And the SAM model, segmentation model, was basically can be understood as 3 models combined and trained together. The first one is the image encoder. This is the VAT, the vision transformer that is in charge of understanding the model. This is the heaviest part, the part that takes the most computing, that is heaviest computing, that takes the most time. And it's in charge of finding the relationships between each of the patches of the image, each of the group of pixels of the image. Then you have the prompt encoder. This is in charge of understanding what the user is referring to with the prompt. So it basically is in charge to convert the position of the, if you provide a point, the position of the point into something that can be combined with the characteristics of the image. And then there's the mask decoder. The mask decoder joins the encoded prompt and the encoded image, and then produces a mask, which will be a segmentation mask of the object of interest. For example, the image can be any kind of image. In this case, we have I think it's a bacteria. The image of a bacteria that can be that we need a prompt. The prompts can be provided manually, such as point prompts or bounding boxes, but they can also be provided in automatically. For example, you can provide a grid, and then the model will detect which prompt is more likely to have an object. But we will focus on the human prompts. Another of the key things that was introduced by the Segment Anything paper was what they call the data engine. So in order to get that many data, we remember it was 11 billion masks, and no, 1 billion masks and 11 million images. So that's a lot of data, and they have to they gradually annotated it. So for that, they first had dozens of human annotators just segmenting as many objects as they could in as many images. They then used this subset of images manually annotated to train a first model. So we have a model trained at the first stage. Then the model that we used, the model that they trained, was used to create more masks or more images, and then these masks were reviewed by the same human annotators, creating a bigger data set, because in this is a semi-automatic stage, so it's faster. So once this the mask segmentations were reviewed by the human annotators, another second model was trained, and then this model was used to generate more and more masks fully automatic without the help of a human. And finally, this third data set is what was used to train the final SAM, which we are going to use now. The important we can get an important takeaway here, that the same model that we are training can help us get more data. This, I think, it's really interesting. And with all these efforts, this Meta people managed to get a quite powerful model that is basically, you can see the data sets here, they're very, very varied and different, with a model that able basically to segment, as they say, segment any object that exists or that you can find. For example, it ranging from waste to animals, tree logs, I don't know, cells, whatever. And this is why I say that this model seems to understand what an object is. And being so useful, it was quickly people in science quickly try to apply to different domains, so make it specific for different domains. For example, we have microsam from Konstantin Pap and his students. It's a fine-tuned version of SAM for microscopy specifically. You have also CellSAM, which tries to segment a whole image using SAM, MedSAM, which is for medical imaging, and even you have the segmentation of satellite images. So now that we know SAM, we thought that it was so powerful that we wanted to give the people who don't know how to use Python and don't know how to program, or just are too busy to set up the environments and everything, to use this model easily with a couple of clicks. And we thought that we're better to use it than in the super user-friendly world of Java and Fiji, where they also could use other tools to like fuse and to use the best of both worlds, the best of SAM and the best of Fiji. And we came up with SAMJ, with, again, as explained later, it should be quite easy to install, just in case someone missed the beginning of the talk. If you want to try to use SAM now, you just need to go to the Fiji update site, click on update, add new update site, and just look for SAMJ, click on it, apply and close. SAMJ will be installed, and you need, once it is installed, you need to restart Java, just restart Fiji, sorry. And then go to plugins, open SAMJ, SAMJ annotator, and then you just choose the model that you want and click on install. Again, depending on the hardware, it might take from between 2 and, depending on the hardware, what I mean, depending on how good and how old your laptop is, it might take between 5 minutes to 20, even 30 minutes. Just understand that this is will be downloading almost 5 gigabytes of data, because it requires to install Python. It's installing a micromap environment. It's installing all the dependencies needed. It is also installing the models that, as we said before, are quite heavy too. But you don't need anything of that. This is done everything by the plugin. So once you click install, just wait and it will be ready to be used. And the idea is that this plugin is as easy to use as possible. You just need to select the image, click on Go. What Go does is this part of the model. So it's doing the heavy part of the model. So again, depending on your computer, it might take more or less time. In mine, it takes less than 5 seconds, I'd say, but I have an old computer where it can take between 30 and 1 minute. So don't be scared of that. If you have a not so fast computer, just choose the SAM2 Tiny or efficient VIT SAM L2. And yes, the idea is that this software is as easy to use as the magic wand or as even the brush. You just need to click on whatever object you want, and then you will get a ROI, a region of interest for it, that you can modify, that you can export, that you can save, that you can analyze. It doesn't matter. The idea is that this plugin is used for annotation, for creating of data sets, for adjusting the easiest way that you can. This is a little bit, I want to explain this, it's a little bit technical, but I think it's important to understand too. So SAMJ, our plugin, is using SAM, which is in Python, but we are on Fiji or ImageJ, which is in Java. So we are bringing, I think we are bringing the most cutting edge, the best of the deep learning world, which is on the most recent and latest technology advancements in this field, which are done always in Python, into the very user-friendly world of Java. So understand that not because it's in Java, ImageJ or Fiji will get old. We will always find ways to bring the best techniques to the Fiji world. So just understand that Fiji is probably here to stay for much more time. And again, I'll explain this. These are the SAMJ functionalities, as the functionalities of the plugin. But in my opinion, it shouldn't, like, I shouldn't even need to explain this. In the end, this is a really user-friendly plugin that you should be able just to use it with a couple of clicks. That there's no need to learn anything to understand the theory or nothing like that. You can just choose the model depending on how good your computer is, or how performance or how difficult your images are. The more difficult the images are, the better the model you would like to use, and the better the heavier model you would like to use. But again, if your computer is not so new or not so performant or not so powerful, you just can choose a lighter model, which work quite good too, and then modify the ROIs using the Fiji tools. It can be used for it. We use the original SAM model, so it's can be used in any image modality. If you wanted, you could even use it in I don't know, in dogs images, but it will work on fluorescence images, on light sheet or whatever. And you have like the different types of prompts that are available in SAM. So you have points, and you have a bounding box, and you have even a brush. And that's here's an example of the usage. See it? So here's the image. You just encode it with a plugin, select the model that you want. In this case, it was efficient SAM. We have it here. We use rectangular prompts, and then this might take about 10 seconds at most. You segment the 4 or 5 cells that you want, and then just export the mask, and then you can analyze it, or you can train fine-tune your deep learning model on that, or whatever you like. Here's the same. This image has some complex shape, but with SAM you can just in a couple of seconds get the mask that you want for analysis, for training, or for whatever you want. And then we prepare a couple of activities. First one is look at this image. There are many cells. So if you didn't have a model for this, or you wanted to prepare a model to find the nuclei in this cell, you would need to spend a lot of time annotating many of the nuclei that are present here. So I'll do the activity with you. You can, if you want, I can send a link in the chat if you want to download this image. And then this one too, which is the next one. And I'll just show you how SAMJ works. So I'll open Fiji. You're seeing my desktop, right? Do you see Fiji? Yes. Okay, thank you. Okay, so we just open the plugin, SAMJ in this case. I have downloaded a couple of models. I have some too tiny and some too large. I think not efficient SAM, not this one. Not this one, but yeah, let's try with some too tiny, which should be the fastest. Okay, let's open the test image. In this case, this one. We can see that this is the image of the example. It's a little bit challenging to segment everything, but we just select the model here, select the model, select the image 10, then click on Go. Remember, Go is doing, you can see it's not immediate, but it's quite fast, at least in my computer. So again, Go is doing this part, the part on the left, which is quite heavy, let's say, but on these tiny models can be done almost quite fast. Once we have done that, we are ready to annotate. We just select whatever we want. In this case, rectangular prompts, and this just annotate the images. We can annotate just the red part, the green part, whatever we want. It should be as you can see, it's quite fast. It's almost immediate. You get the rows here. If you want, you can export the labels too. Like you export as many as the, you can apply then a lookup table or whatever. You have as many as the rows that you have segmented. You can use the point prompt also. You can, I don't know, let's see another area. Here you can provide several points too. This elongated object was a little bit tough. But yeah, you can, it's as easy as one point, other point, other point, that. So you can see it's quite powerful. This image is a little bit challenging, but I think it performs quite well too. Okay, this is the first activity. We're a little bit tight on time, so I'll go to the next one. The next one is just trying to, again, annotate the myelin sheaths in this image, which are the dark areas, which might seem easy at first, but they are not that easy, I'd say. We can try with a tool that is similar to this one. For example, let's try with a magic wand. I don't know if you know the magic wand, but we'll just select some small tolerance and then 8 connected. Okay, so the results are not quite perfect. We can modify the parameters, maybe the tolerance of 10. Yeah, and the results are better, but it's still, depending on where we click, we get one result or the other. And then if we just go to SAMJ and then select the image, click go, again, it's quite fast, the encoding, and then just even with a point, it's annotating, and you can see that the results are quite good. Okay, and then you can basically annotate the whole image in less than, I don't know, a minute if you want, and then analyze it for whatever you want or whatever you just, or use it for the training set or everything. And you have here the possibility to export it, and then you get the labels, and this is it. I'd like to this, okay, I'm a little bit short on time. Okay, so these are the exercises. I'd like to acknowledge this work because it was the work of many people. I think that Arrate already gave a talk in the in place I2K. But yeah, all of them did a great effort, and I think that we did a good job. And now, if you have any question, I can stay for as long as you want, but the talk was supposed to be only half an hour. So please ask in the chat if you have any question, or if not, thank you for listening to me. Okay, so there's a couple of questions now. First one by Nina. How to combine this to train or fine-tune SAM? It is best to use microsam plugin using this to get training data. Okay, so what I think is that you shouldn't try, unless you are Meta or Facebook or Google, you shouldn't try to fine-tune your own SAM. If you want to create a deep learning model, as I said before, you should just try to use a standard, unless if you want to have a model for your specific data. My opinion is best to just use a simple unit, a CNN, ResNet, or whatever, and then use these kind of tools in order to annotate the data, because your model is going to be as good as your data. And with very small models, with very small CNNs, convolutional neural networks, and good data, you will be able to get quite far and to cover 99.9% of your use cases. So it's not necessary to use to create a new SAM or fine-tune SAM. Just use on the zero cost unit, for example, but get decent amounts of data and good data. With, for example, SAMJ, or if you want to prefer microsam, it's also super good. What I would recommend is to try both in your data, see which one you like more, then create your own data set with it, and finally use zero cost or just pure Python or whatever, or BioPy, those no-code tools to train then a simple model such as a unit or a ResNet into for your own data. So yeah, no need to use these big models to train these big models. You just can use whatever is available to fine-tune your smaller ones. I hope it answered your question, or I don't know if this wasn't what you asked. I think so. If you asked, okay, thank you, Nina. And then August, I hope I pronounced good. Okay, so can this be used on 3D data? Not yet. What you can do is to use a stack and then segment it and export it, but it requires a certain certain degree of manual labor. Our idea is to, the objective, we're going to release this version super soon, hopefully within these next 2 weeks. And once this is done, the next key objective will be 3D data. The problem before was that in order to annotate 3D data, you need to encode all the images of the stack, all the slices. And as you have seen, this is quite a time-consuming step. But now with these new SAMJ models, this is much faster. So we need to find a way to make it user-friendly and to be understandable. But okay, so not now, like it's not by default now. It's not supported here, but it will. Sorry for this, August. And I hope this answered your question too. Okay, thank you. I don't know if anyone else has any other question or has tried to install the model and is facing, or the plugin and is facing any problem or not. If not, I can, and if you want to try this, I can. Oh, that's awesome. That's great. I hope it's useful for you. Asier. Yeah, I will leave my email here in the chat. So in case you want to try it and find some issues or some suggestions, because again, this is still work in progress. We're making an effort to bring it. It's already on the fee update side, but to have a final version that has better support, no errors at all, better support for big images, because you can still use this in big images, but it's not super perfect still. So yes, so if you have any question, any doubt, just feel free to contact me or any suggestion, and it will be greatly appreciated. Okay, so again, I don't know if there are any more questions. Yes, it runs on CPU. The next, so the reason for this is that we want to be able to run on every user computer. But the idea is to automatically, one of the other objectives in the short term is to detect whether there is a GPU or not, and automatically set it up for the GPU. Hello, Sevilla, or Daniel. Yes, we did some experiments with the negative points. It was actually available in the previous version, but I removed it because for this family of models, efficient sum, which is a sum variant, efficient VIT, and SAM2, it was quite confusing for the model. So the negative points in my experience were useful in the first iteration of SAM, but here they introduce a little bit of noise. One thing that you can do, by the way, this supports Control-C, Control-Y, So you can easily add and delete your rows. One thing that you can do is to control click several times on to give several points. So that's it. Thank you, August. And yeah, and the presentation is done. I'll stay here if there's any more questions, but if not, feel free to leave. The idea that it was a short presentation because this should be intuitive and easy to use, and there's no need to dig too deep into any theory or the technology that this is using. So yes, so thank you all. I'll stay here if in case you have any question. If not, I guess that the talk is done. Thank you all. Hope you enjoyed. If you have any question or any suggestion, please email me. Thank you. Juraj. Yeah, I think I missed your question. Yes, if you find an error, please, could you please write or just paste it here? I just saw your question, Juraj. I hope you're still here. I hope it was answered by before about the 3D and 4D images. It's not yet out. It can be used, but it requires some work for. Okay. Thank you. Yes, of course. Of course. I will post it on Twitter too. So if anyone is interested, I can put my Twitter handle here also. And I guess that everyone is done now, so I'll close the Zoom. So thank you all. I hope you find it useful, and please, if you have any doubt, any question, please feel free to email me, to text me on Twitter or whatever, okay? So thank you. Bye, everyone.